Matt Robison, Beyond Politics, and it's time for my absolute favorite guest and topic here on Beyond Politics, the latest in our occasional run of episodes where we put the beyond in Beyond Politics. Every once in a while, like a comet returning to our planetary neighborhood, I like to check in with my friend, John Gianforte of the University of New Hampshire, an astronomy professor known online as the Sky Guy. He's an expert in space, astronomy, cosmology, and most importantly, in teaching those concepts. And he's great at bringing these incredible ideas down to earth. Dad jokes aside, I do these check-ins with John, not just because I love these subjects and I find them fascinating, and I hope that I can help people out there feel as awed and inspired as I do by them, but also because it's been really hard in the Trump era, which frankly includes the Biden era now, for people to put American politics in perspective. And I don't want people to disengage from them, not at all. I want us to engage and feel positive about dealing with the issues facing this country and our place in the world. But it helps me to hit the refresh button on that mentally and to put all of this in some perspective, to recognize that in the grand scheme, our fights and our challenges and our disagreements are pretty small, and the universe out there is pretty awesome. So I hope you enjoy this quick break from our usual fare here on Beyond Politics, and that you all find it as fun and energizing as I do as we step into the new year. All right, let's get right into category one. We're cheating because you and I started looking at this chock full, amazing year of discovery in science, astronomy, astrophysics, the universe, and we decided, can we limit ourselves to 5? And we engineered our way to deciding that it's kind of, if you squint, it's 5.
That's a good term, engineered our way. That's
right,
good.
Exactly. We p-hacked. So we're going to do this as categories. So category 1, it was a big year for the sun, our favorite star. It's good for us. It makes us live. So we have several entries under the big year for the sun. And the first, most kind of well-known one was the Great North American Eclipse, April 8th, 2024, widely viewed. What was exciting from a science standpoint about this? Because it wasn't just pretty. There was some real science that we got done.
Most did not see a total solar eclipse, but we tried to offer the explanations, according to science, what the difference was between a very almost a total eclipse, like 95 to 98%, 99% total, and what the difference between a full total solar eclipse was. And when I think, at least in my case, I was successful with a lot of families and people who took my advice to go to the path of totality, even if it was relatively short as 30 seconds for the total phase of the eclipse. And they said it was worth the 8-hour drive back to the seacoast area where they might have come from to see the eclipse, because it was very different. So that couple of percentage points between a almost full partial solar eclipse and a total solar eclipse was a big difference in what visually they saw. So
amateur astronomers were able to add some data for scientists about the corona and add some measurement and data that helps astronomers better understand the cycles of sun activity and in general undergird our understanding of solar dynamics.
The best time to see the corona, the atmosphere of the sun, is during a total solar eclipse. So you're exactly right.
Fast forward 6 months, and the sun had another kind of display, an awesome display, with an aurora reaching all the way south into Mexico. What on earth happened with this? Why were we seeing an aurora? It's supposed to be the northern lights. That's not north.
That's a very good point. And you pointed out that how important the sun is to our existence. And of course, no doubt about that. But 2024 brought with it a peak in solar activity that goes right along with the sun's 11-year cycle of activity. We reached a peak where there was more than 200 sunspot groups visible for long stretches. There had been 0 days in 2023 and 2024 where there were no sunspots.
Mm.
During a solar minimum, which will happen about 5.5 years from now, between 5 and 6 years from now, there could be a year or two where there are no sunspots visible, indicating a lower level of solar activity. So you could say, like you almost said, it's 2024 was the year of the sun. And not only did we see a solar eclipse, many of us, but the solar activity was at a peak. We saw northern lights in New Hampshire in May, and we got a
Wow.
huge burst on the 10th of October when people all over the state and beyond saw this dynamic, beautiful, colorful, vivid display of northern lights or aurora borealis.
Let me ask if I'm sort of understanding this right, because it's interesting and it's subtler than seeing an eclipse. When you see the aurora borealis, the northern lights, or it could be the southern lights if you're in the southern
Yes.
hemisphere,
Yep.
what you're seeing is, so in this case, it was caused by a coronal mass ejection, a burst of plasma from the sun's surface, because the sun is at a peak of activity and it has like storms, it blows up. And what that caused is an interaction with the Earth's magnetic shield, essentially. And so that's what you're seeing, is that interaction of highly charged particles interacting with the magnetic field around the Earth. But I used the word shield a moment ago, and I was talking about how the sun is what causes us to be alive. It creates most of the energy that we use on Earth, that life uses on Earth. But the magnetic field is also incredibly important for life on Earth. We wouldn't have life as we know it without that magnetic field
No,
to
we would
protect
not.
us from all of that ionizing radiation that would break down our DNA and mess with our cells. And so what you're seeing there is an interaction between sort of the life-giving force of the sun and the life-giving magnetic field of the Earth. It's kind of interesting on a deep level.
Yeah, and very few people really know that. And it's actually the Earth has two shields that protects us from the bad stuff that the sun emanates. The sun emits lots of different kinds of radiation. The light that we see is just one kind of light or just one kind of radiation that the sun emits. But the sun emits X-rays, right? You've gotten the sunburn before, right? So that's ultraviolet radiation. It's more powerful, more energetic than the
Mm.
kind of light we can see. But the atmosphere of the Earth protects us from ionizing radiation like gamma rays, X-rays, and ultraviolet rays. That's what the atmosphere does. So at the surface of the Earth, we don't see any gamma rays, we don't see any X-rays. I'm sorry, we don't see any X-rays, and we have only a small portion of the UV that's produced by the sun reach the surface. But it's enough to give us a sunburn. That's why we wear sun protection, because some UV does trickle through the atmosphere. So the atmosphere, the gas, that the oxygen and nitrogen and other gases that form the Earth's atmosphere block or absorb most of the ionizing radiation from the sun. But the sun also emits a wind of charged particles called the solar wind. And this wind blows like between 400 and 800 kilometers per second of charged particles, like alpha particles, like protons and electrons. So these charged particles moving at high speed, that would prevent large organic molecules from forming on the Earth. And that's where the magnetic field comes in. The magnetic field is a shield against the particles that make up and constitute the solar wind. So without the magnetic field, it's the life on the surface of the Earth is history. And Mars, that has no magnetic field, has no shield from the solar wind. And when we first started exploring Mars, looking for organic compounds, we were surprised because we didn't find any. We said, what gives with that? Sometimes we see meteorites that fall to Earth, they have organic compounds inside them. Why did Mars not have any? Come to find out, no magnetic field, no shield from the solar wind. And so we have a sterile surface. And the Earth would be that way too without its magnetic field. So the combination of the Earth's atmosphere and the magnetic field creates this nice place where highly dangerous ionizing radiation and charged particles carrying a lot of energy are prevented from reaching the surface.
It is amazing how what are essentially grand light shows in the sky also reveal a lot of deep science underneath them that have everything to do with the planet and the deep past of the planet and the formation of the planet, which is what caused the iron molten core, which is what causes the magnetic field. And there's so much going on under the surface. Obviously can't get into all of it, but it really is fascinating. And
But we should send a probe to the sun to study more about the sun, shouldn't we?
Funny, there's a joke. Funny you should mention. Funny you should mention. We did this. The Parker Solar Probe. Parker. That doesn't sound like a particularly like deep scientific name, but hey, it is. NASA's Parker Solar Probe mission is just. We're recording this on the 27th, so 2 days ago, 3 days ago, Christmas Eve. The probe got closer to the sun than any other man-made object before. It came within 3.8 million miles of the surface, and that may not sound that close, but that is close. That is really close. I guess no early data yet, right?
We did hear from the spacecraft after it made this close approach. Now, NASA hadn't heard from the spacecraft since December 20th. So late last night, just before midnight, technically on the 26th of December, it got a signal from the spacecraft telling scientists and engineers that the spacecraft had survived this closest approach to the sun. Now, when you say 3.8 million miles, and then you say that sounds like a lot, but it's not. It's actually within the atmosphere, the corona of the sun. So,
and it's hotter in the corona than it is on the surface.
The surface of the sun's only a little less than 6,000 degrees.
A bare trifle.
Yes.
Actually sounds attractive to those of us in the Arctic Northeast right now, but it's hotter in the corona. So this is some heavy duty probing we're doing here.
Yeah, and it's several million degrees in the corona, depending on distance from the sun and what kind of mood the sun is in, because sometimes the corona can get a little cooler, a little warmer, and it changes its shape. As anyone who has ever seen a total solar eclipse has noticed, the corona does not look the same during different eclipses because the sun is a dynamic star. It changes not by the year or the decade or the century, but by the minute.
We could talk about the sun for an hour, for many hours, but unfortunately, we've got to move on. And the way we're going to do this top 5 list, boy, what a podcast gimmick. We're doing a top 5 list. I mean, you and I came up with 50, so we're really cheating here. But the way we're going to do this is we're going to travel ever outwards. So let's move slightly outside the sun to the greater solar system. It's been a bang up year for the solar system as well. A lot. Talk about dynamic. A lot going on in terms of activity and discovery. Let's hit first the brightest comet that we've seen since the Hale-Bopp almost 30 years ago. I'm going to mispronounce it. It is the Tsuchinshan Atlas comet, and we saw it. When did we see it this year? It was September, late September.
Yeah, September. It made its closest approach to the sun in late September, and then it made its closest approach to Earth in October, early October, mid-October, I guess. And all through October and into early November, it was prominent in the sky. And it reached the point, Matt, where it was naked eye visible, which means without any optical aid, like binoculars or a telescope, you could see it. But it was a little tricky because it played hard to get because when the comet is close to the sun, it's at its brightest. It feels the effect of the sun's heat and radiation more, but unfortunately, the sun's brightness makes it tough to see. right? Because the sun's so bright. So it's tough to see a comet in the daytime. But when it finally rose, it gained enough distance, angular separation from the sun in October. Then, after a little after the first week in October, it got enough distance from the sun where we could actually see the comet at dusk, just after the sun set and as the sky darkened. And that really revealed it so well. And it was so bright, like you said, it was the brightest comet since Hale-Bopp in 1997. And I got so many pictures from people who emailed them to me that they took of the comet with their cell phones.
Wow.
So that was amazing. And
That's
it
really
was
fun.
all during the time when we saw the Northern Lights on the 10th of October. We were looking at our best views of the comet, which was wonderful.
My favorite thing about the comet is that whenever there's a comet story, the science writer involved has to put in the fact that it probably emanates from the Oort cloud, which is my sneaky favorite term in astronomy. It's my secret, like, I'm a little obsessed with the Oort cloud. And the Oort cloud, I love this. So some people, especially when there was all the discussion of New Horizons and Pluto, and there was some public understanding of the Kuiper Belt, this idea that there's this ring of icy objects far away, some of which we can see, some of which we can't. And sometimes we get little images, and we had a flyby, and one of them looked like a dumbbell. Well, the Oort cloud looks at the Kuiper Belt and says, hold my beer. You've got nothing on me. It is, if I understand this correctly, it is thousands of astronomical units away, an astronomical unit being about 93 million miles. So we've got this cloud of icy objects that is the source of the comets that we see. And occasionally something gets perturbed by gravity and it gets sent on an inward trajectory toward the sun, and it gets into a rotation and flies by, and we get to see it. And what's amazing to me about the Oort cloud is that it was hypothesized back in 1950 on the basis of, we can't see it, but we can kind of guess based on the ellipsis that's formed by passing comets where these things must come from. And therefore, we kind of guessed. We've never observed it, but we're pretty confident that it's there. We've got this cloud of stuff that's millions of miles, hundreds of millions, billions of miles away, and we're never going to see it. We're never going to be able to see it unless Voyager gets there in 300 years and does a flyby. So it's
Wow.
absolutely incredible.
And it's interesting because, like you said, no one's ever seen the Oort cloud simply because it's so far away. But if you think about it, if you want to talk about sources or reservoirs of comets in our solar system, we have the Kuiper Belt, which extends outward from the orbit of Neptune and is a plane. If you can imagine the solar system being a donut with
Right.
all the planets and the sun at the center in the donut hole, right? And the donut itself, you can think of that as a plane where Kuiper Belt members exist. These are the small, icy, rocky bodies that you talked about. Pluto is a member of the Kuiper Belt, and so are many of the dwarf planets that are at extreme distances from the sun in this flat plane of objects. Thousands, hundreds of thousands of objects, all pretty small. But the Oort cloud, I mean, that's probably, the Kuiper Belt is about 50 to 150 astronomical units out from the sun, which you could think of as kind of pretty close on a large scale. But the Oort cloud, that could be as much as a light year. That's 64,000
Wow.
astronomical units from
Wow.
the sun.
And
So
it
the sun's gravity still
still
has
has an effect. Wow.
that's what I find amazing.
That's
So the
amazing.
sun still has a gravitational capture hold on these objects that sometimes a passing star will dislodge objects from the Oort cloud. And the Oort cloud isn't a disk, it's a sphere, like you said. It's a spherical distribution of small cometary bodies. So we can tell the difference between a comet from the Kuiper belt and a comet from the Oort cloud because the Kuiper belt comets have periods that are generally less than 200 years. But because the Oort cloud is so much further away, if a comet has a much longer period than a few hundred years, and its angle of incidence to the inner solar system, if it's highly inclined, right, it's coming down or up at a steep angle, we know it's not from the disk of the Kuiper belt, it's from this spherical cloud of small icy bodies.
I think one of the reasons that I find the Oort cloud just inherently interesting is that it's the result of a detective story. It's the way you just described that is the way science is most fascinating is when you use little bits of evidence and you kind of construct a picture and we have high confidence in it, but we can't observe it and it's pretty amazing. By the way, since you invoked the name of Pluto, let's talk a little bit about the number of planets we have. Now, for those of us of a certain vintage, like you and me, we grew up at a time where we were told there are 9 planets. Only a fool would count any different number than 9. And then I remember I had like a card game growing up that involved the number of planets and you'd travel to them and Pluto was out there, okay? Then a few years ago, scientists said, no, Pluto is not a planet. It's a dwarf planet. Only a great fool would believe that Pluto is a planet. Then we had the New Horizons fly by and it was like, whoa, Pluto's fascinating. Are you sure? Maybe we want to think again about like dwarf planets. Like maybe we can upgrade them a little bit. I mean, this place is amazing. But anyway, it stays a dwarf planet. But now scientists are getting a little feisty again about the idea that the number is 9 because there is mounting evidence based on gravity and perturbations of various heavenly bodies that maybe there is a 9th planet out there. What do we know? And kind of per the Oort cloud, what are we sort of inferring right now based on the evidence that we can see?
I'm wondering if I should withhold a comment that I am dying to make.
Make it!
I think I'll see how this goes. Well, so I have a set of cups and it has 9 cups. So I know there are 9 planets. Okay. There's one for every planet that we grew up with, right? And in 2006, when astronomers got together and said, we really don't have a definition of what a planet is, let's make one up. Anyway, that ended.
They put Pluto in the friend zone, basically. Yes.
So
sorry, Pluto.
I don't know. So we all have our favorite Pluto stories, but there's a scientist at Caltech. His name is Mike Brown. So he wrote a book and it said why I killed Pluto and why it had it coming, right? So that he did. I read this book. So he is the person that put the nail in the coffin of Pluto not being a planet, because not that he alone made that decision. It was made at the International Astronomical Conference in 2006 that they voted on a definition and it didn't include Pluto. Okay, all right, we're still sore about that one because Pluto was the only planet discovered by an American astronomer, so naturally Americans are kind of ticked off about that. So, okay, let's go with the IAU definition of a planet. Pluto is not one. But Mike Brown, the same Mike Brown, okay, who killed Pluto as a planet, has this notion that, yeah, there is a 9th planet, and maybe he just wanted credit for discovering the 9th planet. So he has this theory, not he alone, but he and a colleague of his, Konstantin Batygin, have this notion that because of the motion of some of the larger Kuiper belt objects, these same objects that we were just talking about, in the area of space around and beyond Pluto, in this disk of objects, they see a pattern, at least in the data that they collect, they see a pattern in the motion of these Kuiper belt objects that to them indicate that the cause of that motion is a large, massive object at great distances from the sun, maybe several hundred astronomical units, that has a mass of a planet about 4 times the size of Earth, about the size of Neptune or Uranus. So that's their notion. Based on the motion of these worlds, these Kuiper Belt objects, there seems to be something making them move the way they do. And their best computer simulations, taking into account all different kinds of parameters and variables, indicate a large massive object beyond the Kuiper Belt that is influencing their motion. And that's the essence of the most recent Planet 9 quest that they're at the heart of.
So those old cartoons where you had Marvin the Martian and you had Duck Dodgers in the 24th and a half century going to find Planet X. You're telling me there really is a Planet X and it's out there. And the best guess from Mike Brown, the Pluto killer, I love the metaphor of the idea that he kind of put Pluto in the friend zone. And now he wants to upgrade to a trophy planet that he thinks is hotter. So Mike Brown is saying, like, hey, there's something out there. It's big and it's 20 times further from the sun on average than Neptune. And therefore we can't see it, but we're pretty sure it's there. I mean, Mike, you're onto something. I'm still not over what you did to Pluto because I ride or die with Pluto, but this is awfully intriguing. Hey, let's do one more in our solar system backyard. There's some new moons. We found new moons this year around Uranus and Neptune. And yes, for our younger listeners, that is the correct pronunciation of the planet Uranus. We found 3 new moons. That's weird. We keep finding moons, although I guess it's not that surprising that we're only finding them now because one of them is only 5 miles across. It's pretty amazing. We keep finding moons.
So here's the thing. From spacecraft flybys of the planets, right? All the planets have been, including Pluto, which is a dwarf planet, have been flown by at least once by a spacecraft, right? And the best way to find small orbiting bodies around a planet, namely moons or natural satellites, is to go to that planet. But even when you fly by a planet, if you don't spend any time there, you could easily miss a small 5 or 10 or 15 mile across moon, right? So when there's a lot of data, even from the Voyager missions that were in the launched in the late 1970s and made passages to Jupiter, Saturn, Uranus, and Neptune, they weren't analyzed. There isn't enough time or money to have people search through all of the data that was collected to look for very small moons that may have only shown up on an image or two or in some other experiment that didn't give a visual picture but indicated the presence of an object orbiting the planet. So as grad students take on projects for their theses, right, they'll say, let me study the Galileo data on Jupiter, okay, and see if I can find anything new. Okay, that's like not exactly how it works, but when students take on a project, they do have the time to go through these older records, old data collections, and spend the kind of time that's necessary to find these really small needles in a haystack. So that's one way of reanalyzing previous planetary flyby data. That's why these new moons are discovered. And also, we have greater technology like the James Webb Space Telescope that can see more clearly and make discoveries that we weren't capable of making back 10 or 15 years ago.
Speaking of the James Webb Space Telescope, let's move on to our third category. And I guess I got to force myself to pick up the pace. Again, I could spend the rest of the show on the solar system, but let's move outward a little bit. It was another fascinating year of discovery from the James Webb Space Telescope that just marked its third anniversary of bringing back incredible data from around the universe, literally around the entire universe. We have a three-pack of incredible images and findings. Maybe I'll just mention two of them quickly and we can splash them up on the screen if we have some editing time here. The clearest picture yet of the Horsehead Nebula, an image of the Cigar Galaxy. That sounds very relaxing. The Cigar Galaxy M82 in Ursa Major. But I have a feeling that the highlight for you was its finding of a star in the constellation Taurus, HL Tauri, showing evidence of water vapor in the young protoplanetary disk. Walk us through that one a little bit. Why is that so significant?
The image, the most recent image of this star HL Tauri in the constellation of Taurus, it's too dim to see unless you have a really large telescope. But we know that our best models of solar system formation say that planetary systems form in clouds of dust and gas called nebulae. And there's a process whereby stars form, and depending on the density and a bunch of other parameters about that cloud of dust and gas, that planets form around the star. And they actually used a radio telescope in the southern hemisphere called ALMA. So it detects radio waves that are in the millimeter wavelength. Okay, that's like microwaves. And they created an image, a visual image from these radio waves that show this star, HL Tauri, at the center of a flat disk of material that is revolving around the star. And the image is so crisp and clear that they can see the lanes, right? The future orbits of future planets as those planets materialize and form.
Wow.
While we watch. Of course, this is a long process, and we're only looking at snapshots of it. But through this ALMA radio telescope, we've detected and analyzed and detected water vapor in this protoplanetary disk. A protoplanet is like a baby planet that's in the formation process. And one of the mysteries or questions is, how prevalent is water in these clouds? Obviously, life on Earth depends on water, and the Earth has a lot of water. Where did the water come from? Right? Because when the solar system formed, Earth was close to the sun, and it's too hot for water, right? The sun's heat literally blows the water away. So finding water vapor in one of these planetary disks that is the actual process of planet formation is a huge discovery and a huge piece of important information for scientists trying to piece together some rules of planet system formation, right? Now, we think we have a good idea of how solar systems in general form. Like, we have a great theory called the nebular theory that explains our solar system. We have 4 rocky planets close into the sun: Mercury, Venus, Earth, and Mars. Then we have this asteroid belt with a bunch of little pieces in it. And then we have these big 4 gas giant planets: Jupiter, Saturn, Uranus, and Neptune. But of all the 5,300 other solar systems that we've detected and confirmed, there's not one of them that looks exactly like ours. Now, what's up with that, right? So that means that our theory of how solar systems formed has a lot to be desired. Nature has a lot of tricks in her bag of tricks on how to make solar systems. And we're in the early stages of trying to figure how that system works, because sure, the nebular theory does a pretty good job of explaining our solar system. But what about all the other ones that we found? And we found lots of systems out there that have multiple planets, more than 5 or 6 planets. So we know there are other solar systems out there, but none of them is structured uh, exactly like ours. Rocky planets close in, gas giant planets far away. We find all different combinations. So we have to, first of all, understand that maybe there's more than one set of rules for making planets, because the environment that the system forms in might be calling the shots, right? So, I mean, every system is going to have its own natural history from how it formed. And that's what we know very little about all those conditions and parameters that exist in all those different solar systems. That's what makes this field of study really interesting and exciting.
And scientists love getting data that presents a bit of a mystery because it sets you up for the process of science, which is essentially, if you boil it down, you form a hypothesis, and
Yep.
then you try to find evidence that disproves that hypothesis. And each piece of evidence that you pile on that doesn't disprove, remember, don't use no double negatives, kids, that doesn't disprove the hypothesis adds some piece of confirming weight, but you never really prove to 100% certainty. You just keep piling up more and more evidence. But when you find something that disproves, that runs against the grain, it sends you right back to the lab, and you've got to rethink everything that you thought you knew. And that's the exciting part. That's the puzzle forming part. And that's, by the way, what's going on right now. Speaking of the James Webb and moving on to our fourth category, that's what's going on right now when it comes to our theories about the very earliest stages of the universe. And we've had a rush of images and discoveries this past year when it comes from the very dawn of space and time. And you wanted to speak to the headlines have been largely around earliest galaxy. There's always a new record being set by the James Webb for the earliest galaxy yet imaged. And we have some interesting issues developing around, we're seeing these galaxies a little earlier than we expected, meaning something is going on and driving the process a lot faster than we thought was possible. The other thing that's going on that may be related is that we now have seen a distant, early, supermassive black hole merger going on 750 million years after the Big Bang. All right, so many questions about this. What's a black hole merger? Is it a hostile takeover, or is it like a friendly merger like Honda and Nissan are doing right now? And why is it so significant that we're seeing a merger of black holes and this early in the evolution of the universe?
Probably 30, 35 years ago, astronomers discovered that most galaxies have at their centers a very large, massive black hole. Now, if we can simplify it to quickly, there's two kinds of black holes. One type of black hole formation we understand pretty well. When a massive star, much more massive than the sun, runs out of fuel, and gravity wins the tug of war that actually started the formation of the star and contracts that massive star that used to be producing energy that helped keep it a star. Once that source of energy goes away and the star explodes as a supernova, the remnants of that supernova can become either a neutron star or a black hole. Those kinds of black holes are called stellar mass black holes. In other words, black holes that form from the process of stellar evolution, star evolution. But scientists have discovered that there's a different class of black holes that are many, sometimes millions or even billions of times more massive than the sun. So we use sometimes the mass of the sun as a unit of measure of mass. So we found that in most galaxies, in the nucleus of the galaxy or at the center of the galaxy, there's a supermassive black hole with millions or billions of times the mass of our sun. So that's one thing. That's one thing. And it sheds some light on the process of how galaxies formed. So some of the trouble that the James Webb Space Telescope has created for astronomers, especially galactic astronomers that try to explain what galaxies are, how they work, and how they formed, the James Webb Telescope, we seemed to indicate that at a much earlier epoch in the universe's history, galaxies were already formed, right? So when the Hubble Space Telescope was launched, it could see far back into time, because when you look into space at great distances, you're actually looking back into time. So the Hubble Space Telescope can bring us back so distant to a point in space that it's maybe less than a billion years after the Big Bang. Now, I know a billion years, one with 9 zeros, that's a lot of years. But considering the latest estimate for the age of the universe, 13.82 billion years, a billion years is almost all the way back to the Big Bang, the event that supposedly formed our universe. So that's what the Hubble did, a little less than a billion years. And it saw what made sense to us was very early stages of galaxy formation, just loose blobs of gas and dust just beginning to form into large structures that we know today are galaxies. When the James Webb Telescope came along, it brought that time back to between maybe 800 million years after the Big Bang, back to about 200 million years after the Big Bang. And what it saw that kind of unnerved astronomers was, wow, we're seeing galaxies that formed only 200 to 300 years after the Big Bang, and they're too evolved. They look too much like modern galaxies that are 12 or 13 billion years old. We didn't think that galaxies should be so bright, that is complex, so early after the Big Bang. That's what we first thought when we initially looked at James Webb data. But they were a little bit relieved because, oh, these galaxies aren't as bright as we originally thought when we looked at the James Webb data at first. But what they did find was that supermassive black holes could have spurred the formation, helped the development and formation of galaxies. And that's what made them look brighter earlier than what we thought they should look that big and bright. I know that's confusing. I'm confusing myself when I'm actually saying it.
No, that makes
But
sense. That makes sense.
so all along, galactic astronomers want to know, how did the first galaxies form, which is still a little mysterious. We don't really know, but we do think now, hypothetically thinking, and as you said, every theory begins with a hypothesis, right? And as you collect data, take images in different wavelengths of light, create computer simulations based on what you saw that help you explain what you're seeing, those simulations indicate that black holes, supermassive black holes, with all of their mass, helped draw material in to help and spur and accelerate the formation of galaxies. So that's, if we've learned anything, we're pretty sure that supermassive black holes were an essential element in galaxy formation.
All right. There was so much in
You
that.
started this,
That what
okay?
this is my fault. So what I'd like to do is, remember how Dwight Eisenhower famously said, if you have a difficult problem, enlarge it? That's what I'm going to do. Rather than try to go deeper into the explanation that you brilliantly gave a moment ago, I'm just going to throw more fuel on the fire and take us from the Big Bang Burger Bar to the restaurant at the end of the universe, hat tip to Douglas Adams, because our fifth and final category takes us from the beginning of the universe to the ultimate fate of the universe. And this is part of our approach of expanding the shell ever outward. Because if we're talking about going back 13.82 billion years, or going out 13.82 billion light years, when we consider the future of the universe, we are considering hundreds of billions, perhaps trillions of years into the future. And the question that's dominated cosmology ever since the 1960s, when we confirmed that the universe began in a big bang, and then into the 70s and 80s, when we realized, hey, there's more matter, there's more gravity happening out there than we can otherwise see. So there must be what's called dark matter. We've begun to wonder, wait a second, we started with a big explosion, everything pushing out really fast. But we've got a lot of matter, we've got a lot of stuff, a lot of gravity that should be sucking things in. So what's going to happen in the future? Is there more blowing out, or is there more sucking in? Is the universe going to keep expanding and expanding? Or is it going to eventually stop expanding and crunch and have what's called a big crunch at the end of the universe? Or is it going to have a perfect magical balance between the two and reach some kind of a steady state, a critical point in the universe? Enter into that the concept of dark energy, because, and this goes really deep, and I'm not going to try and go into all of this, especially with you sitting here able to give a much better explanation. But astronomers, astrophysicists began to realize, hey, there's another force going on in the universe. It might be the biggest force. It's an unseen, repulsive energy, dark energy, that's adding to the pushing out. And we're not able to figure out just how much of it there is, how strong it is, how fast the pushing out is going. We have different sets of measurements that give us two different figures. And that's kind of confusing because it matters a lot in terms of the ultimate fate of the universe. And now, this past year, we've developed even more data that's created even more confusion. And so where we're left at the end of 2024 is the biggest question mark imaginable about the ultimate fate of the universe. That's as good a sketch as I can give that's relatively brief, but I'm sure I skipped over what's sort of the piece of that you think should stand out most in people's minds? What's the science of it that's sort of most intriguing to you?
In the late 1990s, two teams of astronomers working with different instruments looking at supernova explosions in different galaxies. They used a different set of galaxies, and there's lots to choose from. They came to the same conclusion, that the expansion rate of the universe today is different than what it was in the distant past, which means the universe was expanding at a slower rate 7 or 8 billion years ago than it is today. So you could say from that, you could say that the expansion of the universe is accelerating, right?
It's
So if I had to
expanding
make
faster today than it was 7 billion years ago. About half the age of the universe ago, something changed.
yeah. So the way I explain this to my students is a lot of times in high school, you'll take a physics course and you'll play with these cars on wheels and you'll run them down an inclined plane and you can figure out the gravitational constant, right, on Earth, right, the acceleration of gravity. You can, by measuring how the velocity of something changes as gravity of the Earth pulls it down. So if you have a car, one of these little toy cars, take a matchbox and set it on a flat level table. None of us would expect that little matchbox car to automatically start moving without anybody doing anything to it. That would be kind of a strange thing to happen.
Yes,
right?
you would leave the house and probably burn it.
Yes. So, but if you take your hand and give it a little nudge, you're applying a force to that car. And if we remember Newton's laws of motion, if we apply a force, F, to a mass, the little car, it accelerates. So force equals mass times acceleration, right? So if we think about that, not in terms of a matchbox, but the entire universe, if the universe itself is expanding and it has some mass, there must be an F, a force, behind that acceleration of a huge mass of the universe. The problem is, the question is, what is that force? And with a matchbox, it's your hand giving it a little shove across the table. But when we're talking about the universe and all the matter in it, all the mass in it, what is making that move faster day by day, accelerate? That's the question. So we've termed whatever that stuff is, whatever that force is, we gave it this fancy name called dark energy. It's energy, it's a force, but we don't know what it is, so we're going to call it dark. Not because it's evil, but because we don't know what it is, right? It's like dark matter. Yeah,
Right.
there's more matter out there than we can see, that it's causing a gravitational effect that we can measure, but we don't know what's causing it. Dark energy is causing the universe to accelerate at a faster rate in the present than it was in the past, but we don't know why. So if we had to make a call today, the current scientific perspective is, from astrophysicists and cosmologists, is that the universe will not ever stop expanding and contract in a big crunch if we had to make a call today, right? So it would continue expanding and maybe at an accelerating rate, but we don't know that for sure. But we would put money, scientists would put money on the fact that it would never end in a big crunch, but would end in like a big freeze, if you want the other extreme. That's the current state of affairs.
And things would just keep receding further and further away until we literally couldn't see anything else in the far, far distant future. And it would just keep blowing out and out forever.
Yeah, and if you were a galactic astronomer, you'd have to like find a new job, right?
This show would be a lot less interesting in a trillion years. What I find, I know we have to wrap up in a second, and I want to wrap up on two notes. One is that we've managed in the last hour to cover just a remarkable amount, and you've covered it so well, and we've really just done a drive-by. We've scratched the surface, and it shows how much we know, how much painstaking detective work, putting together little bits and pieces of evidence and adding them into this massive edifice of knowledge that we've done over centuries, literally centuries. And yet, our best estimate is that 2/3 of everything that's out there in the universe is composed of dark energy, which means, as you said a moment ago, we don't really know what that is. We don't know the nature of it. We don't know how it operates. We don't know why it got stronger 7 billion years ago, which it seems to have. 2/3 of what's out there, we don't know what it is. And it's amazing to me how much more is out there. And I'll just end on this. I was going to put this into a grab bag, but I don't want to overstretch you any further than I already have. I developed my interest in astrophysics and astronomy and space, the universe, from science fiction, from reading at the age that my kids are currently at. And one of the things that I'm enjoying most right now is rediscovering these books, these stories that were sort of the foundation of my interest in all of this, that fueled my excitement about it. And you, as an educator, do this all the time. You get young people engaged in all of this. So part of what I was trying to accomplish in doing this show and all of our discussions together is I just want to put more out there that I'm hoping will grab a hold of people and give them the same level of interest and excitement that I've always had. And I just want to close on this note, because what's been fascinating to me this year is two stories which represent science fiction, the science fiction that fueled my imagination as a kid, coming true. One of them is the launch of the Europa Clipper mission. Fans of Arthur C. Clarke are very familiar with the hypothesis that there's life on Europa, one of the Galilean moons of Jupiter, that it has a subsurface ocean under an icy crust. And we're now sending a spacecraft there to investigate further. And we're going to start to get some data in 2030. And it is beyond exciting. We're doing this, and there's so much strong hypothesis out there that we're going to find incredible stuff. And that's coming true. This was speculation when I was a kid, and it's coming true. And the other one is AI, artificial intelligence, is making its way into every aspect of our lives. And it's making its way into the search for extraterrestrial intelligence. Scientists are actively using artificial intelligence to analyze data from telescopes and to try to sift through and find patterns that suggest where we should concentrate our search for extraterrestrial intelligence. That's something that was hypothesized about in a short story by Isaac Asimov called Feminine Intuition decades and decades ago. And it's something that we're doing and is real and is very exciting and could supercharge our search for life in the universe. So that's my little note of what really stuck with me from 2024 is these speculative fiction ideas coming into reality and fueling the next wave of discussions that we're going to have in the years ahead. Anything else from that stands out to you?
How can I add anything to that? One of the things that I enjoy about doing these programs with you is how well read you are. So it went from reading some science fiction when you were younger to not only reading science fiction now as an adult, but keeping tabs on what's going on. And that makes these discussions much more fruitful and I have to say accurate. So
Well, I appreciate it. Yeah, no, I really appreciate it. And I know that I'm imposing this on the audience out there, but I hope that by bringing your expertise and your skill at explaining these mind-bending ideas to young people, to people of all ages, as an educator, I hope that we're giving people just a little bit of a taste of why all of this is so exciting and so fun. And so, John, as always, I really appreciate you being with us, walking us through all of this, the shreds of what we do know, the possibilities of what we don't yet know. And we're going to have to do this again sooner than next year.
Yeah, I can invite everyone to visit the UNH Observatory on the Durham campus. We hold 2 public star parties every month on the 1st and 3rd Saturdays. In the winter and very early spring, they run from 8 to 10 when it still gets dark early. And then after we change our clocks to daylight savings time, we run them from 9 to 11, and they're free, open to everyone. And it's a great chance to see some of the things that we've been talking about in our programs that deal with space and astronomy. And I was out walking late last night, and there are 4 bright planets in the sky right now: Venus, Saturn, Jupiter, and Mars. And they just look beautiful. And if you want to look at those planets close up, our telescopes can help you get a feel for what they really look like. I mean, and still being a long way away, but getting an idea of what those planets look like with your own eyes instead of looking at a picture on the internet or listening to 2 people talk about it. There's an opportunity for you to experience the wonders of the universe with your own eyes and ask questions too.
And the links for that will be in the show notes on both YouTube and in the pod. And John Gianforte, thank you so much.
With my pleasure, Matt. Great to be with you.